Right, standard enthalpy changes of reaction. So we can look at how the compounds are put together and the values based on the elements in their standard state being added together to tell us the enthalpy of formation for a specific compound. And then we can look at the compounds involved in reactions and figure out enthalpy of reactions that way. So it really depends on the physical state of the reactants and products and then the conditions at which they're at. So delta H with the 0 means that it's measured under standard conditions. So you're at 298 Kelvin, which is roughly 25 degrees Celsius, which is room temperature, and then 1 times 10 to the 5th pascals, or 100 kilopascals. So if we look at compounds forming under those conditions from elements in their standard state, we can notice things about their stability, and then we can use it to calculate enthalpies of reactions. So what we mean by this, let's look at ethanol. Hopefully you remember that eth means two carbons, and then you have 5 hydrogens and an OH to create those 4 bonds both of them need. The elements needed in order to create ethanol, we need 2 carbon atoms, and carbon under standard conditions is a solid. Then we're going to add, we need 6 hydrogen atoms. Hydrogen is a diatomic, so we would need 3 hydrogen, and hydrogen's a gas at standard conditions. Then we have 1 oxygen atom. Now oxygen's a diatomic, so this is the one time that you get to use fractions as coefficients. Now if we add all of that together, we get exactly 1 mole of ethanol. So the enthalpy of formation means that you're forming 1 mole of that product, and then you have the elements in their standard states. If we look at section 12 of the data booklet, we know that the heat of formation for this is negative 278 kilojoules per mole. So that value is given to you. You're just writing out the reaction. So when it says give the thermochemical equation, that just means give the balanced reaction and then give the enthalpy value. If we look at the next one, this is for steam. So that means water, but as a gas. So water needs 2 hydrogens. Well, hydrogen's a diatomic naturally, so we just need 1 of those. And then we need that 1 oxygen again. So we have our fraction giving us our 1 oxygen, and that's going to form water as a gas. Now, if you look at section 12 of the data booklet, you'll see that water is listed more than 1 time, and that's because it depends on what state of matter it's in. Since this is steam, we're going to use the heat of formation as negative 241.8 kilojoules per mole. Now the questions aren't normally like this, where you are just writing the reaction and pulling the value from your data booklet. Instead, we're going to use those values to determine the heat of reaction. So we're just going to take the sum of all of the products based on section 12, and we're going to subtract the sum of the reactants from section 12. So this is very similar to Hess's law. It's just a different form of Hess's law. Remember that products are on the right and reactants are on the left. So when we say products minus reactants, we want to make sure that we add up the product side and then the reactant side. You also have to take into account the coefficients. So we have 3 carbon dioxide, so we're going to say 3 times and then look at section 12 to get the value, negative 393.5. Then we're going to add our 4 waters. Notice that water is a gas, so we're going to use the negative 241.8 value. So those are all of our products. And then we're going to add our reactants. So we have propane, which is negative, we're going to subtract products minus reactants. So we're going to take the value for propane, which is negative 105, And then we can add our 5 oxygens. Now wait, oxygen's not listed on section 12, and that's because it's an element in its standard state. So elements in their standard state have a formation value of 0. Okay, we're not really having to form it. It's not two things combining together to form this element. So it's 0. So we could say 5 times 0. And we get a heat of reaction of negative 2042.7 kilojoules per mole as our answer. So instead of looking at a series of reactions and flipping and manipulating them, we can just use the heat of formation for our different substances. Let's look at another example. Everybody's favorite, ethanol, being burned. We have our balanced reaction, so we're going to do our products. 2 carbon dioxides plus 3 waters minus our reactant, ethanol, which is negative 278. And then again, oxygen element in standard state, it's 0. I'm not even going to include it this time because it doesn't matter. Elements don't matter in this context. So then it's negative 1,234.4 kilojoules per mole.